I'll just go a little. So machine learning really built on prediction, and cross-validation has been really, really effective workhorse. And two statisticians in the 70s invented. And we have seen lots of applications of machine learning. Now it's really coming to science and precision medicine. And the computation aspect of this is the gradient descent, or stochastic gradient descent, I'll touch upon. And in my view, the prediction cross-validation, as I said, are both really in terms of transparency, accessibility, interpretability. Prediction is very easy, at least conceptual layer, to explain. And cross-validation also has its simplicity. Just try to mimic the prediction within the data you have. And huge amounts of data, computing resource, and software. And the frontiers came out, I think, in Zubin talk, that the spatial, temporal, complex data, and also reinforcement learning in Susan's talk. And scaling up computations always here about hardware and all that. So what I'll address here is interpretability and reproducibility, and which is hinting at uncertainty and overfitting, but it's less conceptually complex and it's easier to explain. So that's what So stability principle, I start kind of writing about it. My group has been using this stability on top of prediction for the last almost like decade or so. And I wrote paper 2013, tried to advocate stability as a minimum requirement for scientific reproducibility and interpretability. We had a lot of discussion on interpretability relative to the context, but here I try to pose it as more agnostic, can be built on other methods, and most people agree that's a good thing. So we need to define what's a reasonable perturbation to data. A lot of times people just scramble about data when data is symmetric, kind of ID setting. And also stability relative to models. I'll show you an example of that. And also a lot of ad hoc decisions. I was talking to Tom that people might have did many different versions of processing. Shall we dig that out? Talk about stability. And also clearly define what's the stability metrics you care about. So this is just all help to have things clearly defined so we can have common understanding what we're dealing with. And this is the paper, actually was the Tukey lecture, Bernoulli 2012. And this idea of stability at least goes back to the 40s with Jack and I. Now in machine learning literature, it's called algorithmic stability. Just delete one data at a point, right? And then you have bootstrap, you have cross-validation, and you have model-based perturbation, parametric bootstrap, and so on and so forth. So it's a huge literature that I'm building on. And what I'm trying to also put forward, give a name, is we start with prediction. So it's kind of bring back a lot of the traditional statistical issues after prediction. Use prediction as a benchmark because it's very easy for people to understand. It's very popular. And then bringing stability for interpretability among the best predictive models. We're going to see lots of models seem to work as well in terms of prediction, but they have different interpretations. And this is the first attempt. The paper appeared last year, but the paper was making in 5 years at least. So this is a attempt that we use cross-validation for Lasso, which is L1 panelized least squares, to choose the smoothing parameter, how much constraint you want to put on sparsity. So our idea was to add the stability angle to it. So start with the cross-validation model, and you shrink it until this estimation stability metric, if any mismatch is there, is minimized. So you kind of start with a good place. It's a good prediction model, and you look for sparser and sparser models until the stability metric tells you stop. And for a particular problem, we'll bring work on for movie prediction, that you should see that these different columns are different voxels in fMRI measurement. And the cross-validated selection, all the predictors here can be located on the screen related to a Gabor wavelet, so that's why the dots. So cross-validation can see that seem to suggest, like all over the board, possible driving this voxel in the brain, right? That's suggestive of what Karen said, persuasive, right? That's why I have the evidence. I want to go back to tell people, actually this voxel cares all about it. If we use the ESCV, which is on top of cross-validation with estimation stability, and it shrank tremendously the possible locations. And we don't lose prediction for this case. Sometimes you do prediction accuracy. So this is just more interpretable, and you still keep your prediction performance, And actually, in this case, we believe this is more sensible scientifically because we don't believe the voxel cares all over the place. It's more localized. Right, so this is a case more stability in a quantitative sense. And the second example I want to show you is that we go back to deep learning. Now we try to use deep learning not for self-driving cars, but for neuroscience. We try to use the deep learning as extraction of features and feed into a single neuron measurement. And the data had been collected almost 10 years ago by Jack's lab. We're looking at a very difficult visual area in the primate cortex called V4, which is after V1 is like edge detector and before like object recognition. It's in the word pathway. And the data was grayscaled, cropped natural images. And we have the single neuron measurement, like aggregated rate of spike trains. So here we can say this is transfer learning, because we're going to take a deep learning model trained on ImageNet, had nothing to do with experimental data. And we use it as like feature extractors. And we hope to land some support for the resemblance of CNN to brain. First, benchmark against state-of-the-art prediction model. And for V4 neurons, haven't been a lot of work, and we get the best prediction performance. And now we want to interpret it. And we go for the interpretation that's stable across many models. So this is, previous speaker already introduced the deep learning. I won't say more. So we use ImageNet, had nothing to do with our data, and fix all the weights and do the extraction. I'll take second layer. I'll show you that I get the best performance. I'll tell you about layer 3 and 4 later. And we use very simple linear fitting like Rage or Lasso to feed the neuron activity, which is a time series. It's binned firing rate. Those are the time series. Okay, so the weights are fixed from ImageNet, and then we use it as a black box. And then you have at least deep nets, right? The AlexNet, the VGG, and GoogleNet. And they have different architecture. They have different number of weights. And you can at least use 2 regression methods. So now I want stability across these 6 models, right? 3 deep nets, 2 regression methods, you have 6, at least 6 models. And they all give pretty simple, simpler prediction performance. So my stability measures, one is prediction, I'll show you. The other is actually human visualization of model result through exploratory data analysis. And we're only ready to interpret the patterns as signs that are stable across the different models. So this is, we have 74 neurons. This is the average prediction performance. You can see that definitely V4 is not V1. Gabor-like models, the blue one, you have a big job of prediction performance. But after you went to N2, C3, I'll come back to C3 later. These are just different layers of AlexNet. So let's look at N2. It's the second layer. First, we thought, can we map all the V4 neuron into a particular layer of AlexNet? I'll come back to that too. And the 3 colored the data are the dashed lines. And the 3 prediction models are AlexNet, GoogleNet, and VGG. Okay, so pretty consistent with some variabilities. So that's good news, right? Because they're from the same data but with different architecture. And a summary is that if you look at the relative good performance, this is all the neurons, but some just really bad. So if you take the ones with a sensible correlation, prediction performance, use correlation because we cannot predict the magnitude, then the Ridge of Lasso is kind of elastic, that does the best. Ridge does pretty well, but you have so many number of predictors, so it's not really humanly interpretable by any human. Forget about lawyer or machine learners. I think we're here together. And here then become a little reasonable. Maybe there's a difference. Lawyers want to see 20, and we can handle 100, but it's more reasonable. So the next day, so they all give state-of-the-art prediction performance. I have 6 of them. So what I want to show you is that we want to only look at the stable top regression coefficient. Ridge and Lasso are among the top ones, which are top coefficients for both. And also tuning regions. I don't want to have different understanding which area this neuron cares about, depends on which Google net or AlexNet I use. And also we try deep dream images. That's up there, whether it's science or just fiction, but at least there's consistency. And we also look at activity maximizing images I won't show here. So this is a particular neuron. Of course, we chose one model works pretty well. It's a 7.2, so you can see it's a little one of the best performing ones. And these are the visualized locations where the Lasso coefficients seem to indicate that, well, I care about these locations. And this is the ridge. It's a lot more smoother. And these are the images that seem to drive this model neuron. And you can see that there's all these almost horizontal edges. So we feel like probably, based on this, based on the model we have, this neuron care about activities in the middle and with kind of horizontal direction. And we look at across different deep learning nets, and we're very happy to see that they're not exactly the same size. This is another neuron, that's why I don't see the cross anymore. AlexNet, VGG, and GoogleNet give very similar, we call the tuning region. So how did we get the tuning region? We took the rich version of the model, is that we put like stimuli at these different locations and then see where it's maximized. So this is a typical neuroscience kind of tuning curve extension. So this suggests that neuron C care about these regions. And it's consistent across these 3 different nets. So that's why we're happy to say that this neuron care about this region. And it seems there's this directional preference too. Again, stable across the different net. But the color, we don't want to interpret too much, but you can see it's more on the brownish, greenish color, right? So we're looking for consistent patterns and colors to interpret instead of, let's take this one. We might read too much into this color. So we use stability to give us more, I would say, trustworthy interpretations. But they are not identical, right? So this is human judgment come in. But we all kind of agree they're kind of consistent. Put a like quantitative measure, it can be bad and good, I think. And we also run deep dream patterns, right? I think one of the early speakers went there a little bit. So we start with random starting points. And we have now a model neuron, our model, based on neuron A and B and C. That's the color. And this is Lasso, this is ridge. And these are the local maximums of the images maxed that surface, which is a model. Again, you see neuron A we saw before seem to prefer these slightly tilted edges. But without the tuning region, we wouldn't know that actually neuron only care about this region. So you can combine them together and get it. So this is another way to show that whatever the surface is, this Lasso and ridge-based deep learning with AlexNet, there's some consistency, local behavior. And neuron B, similarly, and neuron C, you can see, we saw that. So these are the evidence. We'll try to put the different metrics together to convince ourselves that there's something we're ready to interpret. And there are more results I won't show you here, is that we did look at, actually I gave this talk in DeepMind in summer, and there were good questions, but how about other layers? 3, 4, and 5, actually they also give similar predictions. But they're much harder to interpret. We don't have this consistency of patterns. But the layers seem to be consistent. It's just, for the things I show you, it's consistent. But a lot of other things are not, I'm not showing you. And we look at the prediction performance stability, use ESCV, and also model size. And we couldn't convince ourselves that the V4 neurons nicely map into one layer. And there's no reason why it should be, right? But we were just looking for neat results. And we only look at layer 2 for a while. So we think that the V4 neurons, the ones is not random selected population, seem to map into different layers, CNN, like layer 3 or layer 4. There's no reason why they should map, right? This is completely, that layer is not validated scientifically. So that's where we are. And the other ongoing project going on with Ben Brown at the IBL and our postdoc who now at Cornell is again build stability to another very powerful nonlinear machine learning method invented by my late colleague Leo Bryman and student Adele Cutler. Random forests have this rule-based like a form, which is a pretty good match, or decision-based match with nonlinear biomolecule interactions, because people tend to believe that when you have certain intensity goes to a certain level and the biomolecules or chromatins will interact. But random forests give very good performance in terms of prediction, but very unstable. When you change the data 10%, do this perturbation exercise, then you get different interactions. So the same idea is that we add stability to random forests. Actually, in several different ways, we did data perturbation. We also did like soft dimensionality reduction by using the importance measures from original random forests and do weighting. So we did many steps, but still add stability. And we're able to get pretty sensible non-3-order interaction in an enhancer status prediction problem on Drosophila. That the first one actually is well known. The second one was discovered 2012, and the third one is our new discovery. It has to be tested by the lab. So this is the things that they are individually not main effects. So if you don't look at interpret in the right way, if you do the polynomial expansion, you won't see them because there's a mismatch of functional form with the problem. If you just do linear main effects, do cross polynomial, things like that, you won't see them. So it's a high dimensional space. The matching of the subject knowledge with the mathematical form, I think does give you a leg up, unless you have really, 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 really outside for the discovery. So in terms of connecting the three things in my title, predictability, stability, and computability, here I take computability as just only iterative learning algorithm and stepwise like convergence. So there's work there between the algorithm stability or jackknife and generalization, and there's also convergence rate and generalization trade-off, and we are working on with my student and to making this connection. But this is a particular form of stability, only the one. And since there's a lot of big picture talking, and one thing kind of hinted at, I want to bring it up to the fore, is the representativeness or the need for design experiment thinking about data collection. So I've been teaching this class with 3 colleagues at Berkeley. It's a new data science 100 class, so I mentioned that in the class, so I have a slide ready, is that the statistician people look at me and say like, well, God, you're statistician, and you guys couldn't do the prediction of election, right? So there are many, many reasons, I think, but one reason, at least this article put forward, is that there were a lot of data in the form of papers from the field that Brooklyn, the headquarters of Hillary Clinton, just didn't enter into computer, right? Because they trusted their analytical algorithm so much. They felt they really optimized. So what my late colleague Freeman would call shoelace work, right, was not respected, and data was not entered. And for this year, the undecided voters was 12%. Previous years, only 4 to 5%. So this alone, if you have no sense about this undecided voter, doesn't matter what fancy and good your algorithm is, you're not going to be able. It was pretty tight race in the end. You basically doomed. But these ground operatives do have information. They talk to people. They have a sense. And those information is qualitative, but was not taken into account. And that's this very basic statistical concept. You want to think about a population, and you want to have your data be representative of what you try to get at. So that's a very conceptual omission. I think a lot of the time to collect data, just, oh, I have more data I have. It doesn't matter. People don't tell you what they're going to do. I think people sometimes too shy this year to tell who they want to vote. So that's just huge. People just don't say it. And then you're not going to get what you want. So this population concept is extremely important, and think about representative. And that's a simple statistical concept I think hopefully will be embraced. It's not exactly fairness, but it's related. So looking into the future, I think machine learning seems from where I stand is turning more statistical and turning more contextual. Basically depends on the subject matter and depends on the context. And precision medicine and election, it's really a one-time shot application. It's not like something you have IT application, just get more and more data, you care about the average prediction performance. You want one time, you have small variance, and other information has to come in, there's no magic. You have to understand the problem, bringing other information in, so you have one-time shot, better prediction. As I said, experimental design in general should be at the upfront of machine learning, representatives of the data. And for precision medicine, I feel like this uncertainty should be individualized. Some people have high tolerance of risk, and they can do more risky treatment. Others, so this false positive, false negative Richard was talking about probably would be individual for precision medicine. And we shouldn't just cut at 5%. And human panel, right? Again, my teaching that I dig into the history about smoking and cancer. There was a study of US Department of Health and Policy in 1964. A big panel of people basically declared smoking and cancer, there's a causal relationship. It was not lab, was not physiology, it was a human decision. And most of us buy that. So I think we might enter more of that. It's like humans have to make important decisions in the end. And in terms of this prediction, stability, and computability flow I'm advocating, I think I would like to see that we have interpretable workflow. A lot of this, even I still write technical papers. And I think if I now work with my students, so we shall probably agree we have a protocol. We shall have narratives to talk about these issues. What's our stability measure? What's our perturbation in a more easily discoverable fashion than hidden in a lot of math and all that. It's kind of there. So you kind of just have more structured writing, I think would really be helpful. And Kara's one there already is that a lot of this can only be achieved when we have education already going in that direction. And the last slide is advertisement for work of many colleagues in Berkeley we have been doing for the last 3 years. We have a Berkeley Data Science Initiative, and the report, I'll give you the link, is there. It's not just intellectual, it's also organizational. Right now, we're in the search interim dean for Division of Data Science. So the idea is that the first mission was education, right? We had this Data Science 100 co-developed by CS staff faculty with 1,000 students a year, and I'm on the team to do DS 100, where we're trying out 100. And it's really this education mission has to be supported by organization change instead of in the old framework. And the links for the report and summary, and thanks to NSF for the Center for Science and Information, and also ENCODE from NIH. Thank you.